Watch this. I have a complete list of data. I make a copy, add one thing to that copy, and when I check my original list, it's been changed. In this video, I'm going to show you exactly why this happens, why the usual fixes aren't enough, and how you can use the right tools to make your code absolutely bulletproof. So let's break down the code that causes all this grief. It looks perfectly innocent. Imagine you have a list representing your team's project pipeline. Now you want to create a second version to try adding a new step. So you do what seems most logical and assign original pipeline to experimental pipeline. This looks like a copy, it feels like a copy, but as we just saw, this is not a copy. To prove it, let's add a new step to the experimental pipeline. And now let's print both lists. You'd expect experimental pipeline to have 4 items and original pipeline to still have 3. But when you run the code, you see this. Our original data is ruined. We changed the copy, but the original changed right along with it. This is the heart of the problem, and it comes down to how Python thinks about variables in memory. So what's really going on here? When you use the equal sign, you're not creating a new list. You're just creating a second name or second label that points to the exact same object in memory. Think of it like this. You have a box in a warehouse holding your stuff. On that box, there's a label that says original pipeline. When you write experimental pipeline equals original pipeline, you don't get a new box. You just slap a second label, experimental pipeline, onto the very same box. Now, it doesn't matter which label you use to open the box and add something, you're still changing the contents of that one and only box. We can prove this with Python's built-in ID function, which shows us the unique memory address of an object. When you run this, you'll see the numbers are identical. Both variables are just different names for the exact same spot in memory. This is why assignment doesn't copy objects, it just creates another pointer to the same object. Alright, so assignment is a trap. How do we actually create a separate object? The first and most common solution is to create what's called a shallow copy. For a list, you can do this in a couple of ways. The first is using the .copy method, which is built into lists and dictionaries. The second common way, just for lists, is to use a full slice. Both of these do the same thing. They create a brand new list object and fill it with the copies of the elements from the original. Now, if we check the IDs, you'll see 3 different numbers. We have 3 distinct list objects in memory. We finally created new boxes. So now, if we modify our copy and check the original, success! The original list is safe. Our change is isolated. For simple stuff like a flat list of numbers or strings, a shallow copy is fast, efficient, and does exactly what you need. It seems like we solved the problem, but this is where the second, even more sneaky trap is waiting. A shallow copy works perfectly as long as your list contains simple data like numbers and strings. But the real danger pops up when you're working with nested data, like a list of lists. This is a super common scenario in data analysis, web development, you name it. Let's model a situation where we're tracking tasks for different teams. Our data is a list of lists. Each inner list is a team's to-do list. Now let's create a shallow copy to plan the next sprint without messing up the current one. We have our new outer list. The ID of sprint plan is different from team tasks. Far, so good. Now let's say the design team finishes the task and we add a new one. We'll modify the first team's list inside our sprint plan. We only touch sprint plan, so team tasks should be fine, right? Let's check and see. And disaster. Once again, changing the copy has mutated our original data. So how's this possible? We know we made a new list. Here's the catch with a shallow copy. It only copies the container. It creates a new outer list, a new box, but the items inside that box are just pointing to the same objects from the original. So team tasks was a box containing 2 other boxes, the inner lists. When we created a shallow copy, we created a new main box, sprint plan, but we filled it by pointing to the exact same 2 inner boxes. We copied the references, not the nested objects themselves. When we grabbed sprint plan sub-0, we were grabbing the very same inner box that team task sub-0 points to. A shallow copy is only 1 level deep. So how do we create a truly independent clone of a complex nested object? For this, we need to bring out the big guns, a deep copy. First, you need to import the copy module. Now let's run the scenario once again, but this time with copy.deepcopy. The deepcopy function doesn't just copy the outer box, it walks through every single thing inside the original and creates a fresh copy of everything it finds. It builds a new box, then looks inside the original inner boxes, and builds new, completely separate inner boxes for our copy. Let's prove it. We'll make the same changes to our sprint plan. And now the moment of truth. Let's print both lists. Perfect. Our original data is pristine. Sprint plan has been changed on its own, just like we wanted. A deep copy creates a completely new object and recursively copies everything inside. No more shared surprises. At this point, you might be thinking, why not just use deep copy all the time to be safe? It's a fair question, but there's a trade-off: performance. A shallow copy's fast. It just has to create one new object and copy a few pointers. A deep copy can be much slower and use more memory. It has to travel through every single element of your data structure and build a new object for each one. For a huge, deeply nested structure, that difference can really add up. So here's a simple rule of thumb. Use assignment only when you want two variables to control the exact same object. This isn't copying, it's aliasing. Use a shallow copy when your data is flat. No nested list or dictionaries. It's fast, efficient, and gets the job done. And use deep copy whenever your data has mutable objects inside, like lists within lists, and you need a completely independent clone. This is your safest bet for complex data to avoid any weird side effects. The whole concept is also super important when you're working with your own custom classes. Let's say you have a user class with a list of permissions. If you make a shallow copy of this user, you'll find that while Bob is a new user, his permissions list is still linked to Alice's. Removing delete from Bob's permission also yanks it from Alice's. But why? Because the shallow copy created a new user object, but just copied the reference to the original permissions list. To fix this, copy.deepcopy on admin user would create both a new user object and a new permissions list, keeping them totally separate. For really advanced control, you can even define your own dundercopy and dunderdeepcopy methods inside your class to tell Python exactly how you want your objects to be copied. Want to prevent some more Python gotchas? Check out this video where I go deep on another topic. If this video helped clear things up for you, do me a favor and hit the like button, and subscribe for more practical Python tips that will make you a better developer. And leave a comment below if you've ever been bitten by this bug. I'd love to hear your war stories. Thanks for watching, and I'll see you in the next one.